All right. So today, one second, let me admit everyone. Yeah. So today, our goal is in a way to kind of have a, you can say capstone to the course, or you could say our goal is to learn maybe the most immediately practical, most immediately applicable part of the course. It's, it is interesting that we only at the very end we arrive at what is maybe mostly applicable to practical use in quadruped robots. Okay, and that is model predictive control and what the original inventors call whole body impulse control. Right? In a way, today's lecture is going to be almost completely based on a single paper written by Kim and co-authors. The citation will be at the end of the lecture slides. And this paper, in a way, established what appears to be, at the moment, industry standard. So this approach to control of robots that I'm going to outline here appears to be a standard approach that teams across the field use. That is my impression. I didn't do a survey, and there are clearly differences between individual approaches in details, sometimes in significant details. But this appears to be universal enough. That is why I think it is practically significant to understand this topic. All right, so let's do it. Okay. So before we can go, we have to one more time consider simplified models. If you remember last time, we were talking about conservation of momentum, we were talking about impact, we were talking about how this idea of impact and the simple gates, how it creates for us formulas to compute next step. You could say it also allows us to compute something like a trajectory for the center of mass, right? We were using linear inverted pendulum, linear spring-loaded linear inverted pendulum, right? Those models, they were very simplified. It's like a point mass instead of a robot. That is what we worked with. Well, today we go a little bit more complicated. Today we consider a robot as a single rigid body, okay? Single rigid body. Okay. The way to think about it is twofold. One way to think about it is that your robot, typical quadruped robots that you're going to work with, would most likely have a body, so a very noticeable, bulky, rigid link. It's very different from any other link. You can immediately recognize it as a body, right? And legs, right? For quadruped, it will be 4 legs. They're usually going to be much smaller than the body. So, like, if you're trying to classify it, so sort of from mathematical perspective, you can ask what makes a body, what makes a leg. But from practical perspective, you can look at a robot, you would instantly see what is a body, what is a leg. For bipedal robots, same thing. If you look at Atlas, for example, any model of Atlas robot, or Asimo if you want, you can instantly see where is the body and where are the legs, you know? So you can think of a robot being a body and the legs. So we can assume that mass and inertia of the legs is much smaller than that of the body, okay? If your legs are tiny, especially if your motors are physically located in the body rather than being located in the legs, if your batteries are in the body, if you have a hydraulics, maybe if your hydraulics are located in the body, etc., etc. And the legs are only sort of structural elements to convert ground reaction forces into forces acting on the body, well, then it somehow makes sense to imagine a robot just being this massive body and with legs whose inertia can be ignored. That is one idea to how we can think about modeling a robot as a single rigid body. You just you have a robot, right? And instead of thinking of a robot as a mechanism with complicated dynamics of the body, dynamics of the legs, instead you say, okay, let's forget about the legs. Let's just imagine that the dynamics of the robot is kind of like a dynamic of a rocket, where you have reaction forces placed at the joints where the legs are. So somehow you imagine that there's a source of reaction force that acts directly where the, let's say, joints are applied. This, of course, is slightly complicated because then you have to consider torques, then you have to consider torques. So instead, you can simplify and say, okay, the reaction forces are actually applied here at the ground level, right? Then your computation of torques becomes simple, and the reaction forces mean what they usually mean, the actual ground reaction forces, rather than internal forces inside the robot. And you can still ignore your legs if they're light enough, okay? So this is one way to think about it. You kind of think of your robot as a rocket with the forces attached to it, okay? Another way is to say, okay, the robot, the legs still have mass and inertia. We cannot ignore it. We still have to take it into account. So let us find a single rigid body whose model behaves in some way as close to the behavior of the robot as possible. So we find a single rigid body who, under same reaction forces, exhibits the same acceleration as the robot would exhibit. Angular acceleration, the linear acceleration. So presumably the mass of this single rigid body would be the same as the mass of the total robot. Inertia would somehow be similar or exactly the same as that of the total robot, and so on and so forth. I apologize if you hear background noise. Okay, cannot do anything about it. Check the microphone. Oh, let me just change the microphone.
From my side, the background noise, it's I cannot hear it honestly. So,
Yeah, the voice is clear.
Okay,
There's
okay. Great. Okay, then I will just keep the microphone the way it is. Okay, good. So you can see two approaches are roughly speaking, they're talking about the same thing. Either your legs are already so light that they don't contribute much to the dynamics, or you kind of create artificial single rigid body that acts kind of the same as the whole robot overall. Okay. But in both approaches, you find a rigid body model to replace the robot. Okay. All right. So a single rigid body, and by the way, sometimes people call it a potato model because you think about your robot as a potato, like a single thing in space without legs. So this single rigid body behaves the following way. Second derivative of your position of the center of mass multiplied by mass, right, would be governed by reaction forces and gravity. That is the second Newton's law. So just sum of all forces equals derivative of momentum, or another way, acceleration times mass equals sum of all forces. Okay, second Newton's law. And here's Euler's law. I'm just not writing it out like exactly here. So what I'm saying is the derivative of momentum. Here I'm kinematic momentum, I think is the correct English term. Somehow feel unsure of my terminology here. derivative of kinematic momentum here would be equal to the sum of all torques, sum of all external torques. What is going on with this Euler equation? Well, this is an inertia tensor. This is your angular velocity. Their product, let's call it kinematic momentum, okay, is an entity. Its derivative behaves in many ways the same as derivative of momentum here, right? It is equal to sum of all external, like in this case, torques. Here, the only torques that we have are the torques associated with the reaction forces. So we assume no direct torques acting on the body. And importantly, we ignore gravity, which implies that the gravity does not provide a torque, which would imply that the coordinate system is chosen in such way that the torque associated with gravity would be zero. So you have to be careful about the choice of your coordinates if you're going to follow the formula 2. Of course, you don't have to follow the formula 2. And in general, your attitude towards formulas like this should be to always keep in mind assumptions which are quite obvious here, right? Like this is not alien math. It is basic classical mechanics. So in your case, when you are going to implement something based on this math, you can simply go from definition of Euler dynamical equations and check what you have. I don't think it is the correct approach to just copy it. Okay. For example, you have to wonder in which coordinates inertia tensor is expressed, in which coordinates omega is expressed, in which coordinates all of those are expressed, right? And so on and so forth. So you have to be careful. It is not a source of big headaches. It's just basic care that you need to take care. All right, but the important message is this is the second Newton's law and dynamic Euler equations of dynamics. Basic stuff. Basic stuff. Do you have questions? No? Okay. Okay. Well, this is what we are going to use as a model of the walking robot. This, in a way, at the same time should be exciting because this is simple, and this is what we studied in our introductory courses on classical mechanics. Hopefully, you had it in the university course. And even if you didn't have it, this is one of those topics which are amply covered by literature and online lectures. So this sounds like something that should be very easy to work with because of how basic those equations are. The way I've wrote it might be making it sound a little bit too basic, and that is because I didn't open this derivative. And if I did attempt to open it, you would have to ask me in which coordinates this I is expressed. And this would lead basically to slightly more complicated, slightly more complicated results than what we have here. So this equation is not so basic, but basically it should be exciting. It should be promising us easier life. Okay, that is one thing. Another thing, of course, is we have to be a little bit worried about how accurate this is. Okay, how accurate it is. We'll see at the end of the lecture exactly how we use this model, and why we want it, and where we give up on accuracy. Okay. Now let's spend a little bit of time understanding what's going on. So this equation is linear relation between acceleration, so p double dot, and forces Fi. So those entities relate to each other linearly. M cannot help but being a constant scalar, so we cannot expect any bad behavior from M, and we don't have anything else. So those relations are linear, and linear equations of this type are perfect as constraints for convex optimization. SOP, convex optimization problem. So linear programming allows those constraints, quadratic programming, second order cone programming, semi-definite programming, and so on. Every type of convex optimization problems would readily allow those constraints. Moreover, they can be solved analytically sometimes with the linear algebra. So it's very nice, it's very good. So far, we don't have any issue when we look at those constraints. Okay. Now let us, for contrast, look at this equation. And here I will only look at the right-hand side. I would ignore what's going on the left-hand side. The left-hand side is a separate can of worms. It also can cause us all kinds of problems, but let's ignore it. Let's just consider the right-hand side. So the right-hand side here is bilinear. So there are two components, Ri and Fi, where Ri is a position. You could say it is the vector that points at the point of application of the force. But we know what is the point of application of the force. That is the point of contact. The vector comes from the center, like from the origin around which we measure this equation, Euler equation. So, for example, from the center of mass, right? Since we remember that gravity somehow produces zero momentum, it is reasonable to assume that we measure this whole story relative to the center of mass. All right, we construct dynamic Euler equation using the center of mass as the origin. Okay, so Ri could be vectors coming from the center of mass to the origin, sorry, to the contact. Those Ri and Fi come linearly into the equation, but the equation both is bilinear in those terms because cross product is a linear operation. Okay, it is a linear operation between two vectors, and the result is a bilinear function of those vectors. So if you fix one of them, if you assume that one of them is a constant, like reaction force is a constant, then it is a linear function of Ri. If you say position is constant, then it is a linear function of Fi, reaction force. Okay. This is not an easy thing to work with for a convex optimization problem. Okay. And it would be easy if at least one of those two would be constant. Then it is linear, and linear is easy for us. But if it is not, if none of them is constant, then we cannot do our classical like convex optimization problems with such constraint. In fact, equality constraints only work for linear functions. Equality constraints don't work for anything else. We cannot have quadratic equality constraint usually, right? We cannot have or anything else. And bilinear cannot have either. And this makes sense because such equality constraints, by definition, describe a non-convex surface, right? If you remember, definition of convexity is that if two points are in the domain, that everything between them is also in the domain. And this definition sort of tells you that the domain has to somehow resemble linear space, right? And if your equality constraint has something nonlinear there, for example, like a circular, describing a circle, like x squared plus y squared equals to something. Well, clearly, if 2 points on the circle wouldn't have everything in between them to be also on the circle, right? So it is not a problem of how we write the equation. It is the nature of the problem that this equation of torques associated with reaction forces, that this equation is somehow not suitable for convex optimization. Okay. It is the fact about the problem itself, not so much about how we write the problem. Okay, all right. Now, this bilinearity has consequences. One consequence is if we're going to do trajectory planning problem, right? So we're going to just generate a trajectory for a robot. Let's say a robot described by this potato model, SRB. So single rigid body, right? Then it means we cannot use convex optimizers. We have to do nonlinear solvers. So something that can be close enough to a convex solver, but not a convex solver. Okay, so iterative approaches are popular, such as iterative, what do you call it, sequential quadratic programming. Okay, or interior point method solvers that operate on non-convex domains. Right, so you do interior point method, but on non-convex domains, those kind of things. And they have common problems of no guarantees of convergence. Being stuck in local minima is a scary potential problem, and so on and so forth. So while it is possible to do it, it's just not something that you want to have to do. Sometimes you have to do it, and most of the time, TPP, this trajectory planning problem, for working robots is done exactly like that. You solve nonlinear optimization. You don't try to do it convexly. Okay. There are all kinds of ways to do it in a nonlinear way, right? You don't have to straight up write this bilinear equality or anything like that. But at the end of the day, almost every type of trajectory planning problem is non-convex and is done with nonlinear solvers. As far as I know, that's not my area of expertise, so I'm giving you kind of like, you can say my impression. Okay, good. Now, for problems that have to be solved with the convex solvers, for example, MPC problems, they have to be solved with convex solvers because otherwise they're going to run forever and you'll have trouble. Okay. You prefer to solve MPC at high frequencies, so you have to either solve them directly with a convex solver, or if you want to be them to be nonlinear, you want nonlinearity to be extremely small. Okay, like very limited nonlinearity, but preferably you want it to be convex. Okay, so for those, what we typically do is we assume that the contact points C are R sub I, so R sub I are fixed. Okay, so we say that those are not decision variables; those are known in advance. And this would make the right-hand side of this equation into a linear function. Now, when I say that the contact points are fixed in advance, what you have to ask is, but how do you know them? Where do you get them? And there is an answer which you could, I mean, there are multiple answers which you could use. One is to say, okay, I will just create a law of how they are found. For example, my step is 30 centimeters forward, and that is it. That is a law. So the robot goes 30 centimeters forward, 30 centimeters forward, 30 centimeters forward, and so on. Is it going to be a good law? Maybe not. But you remember last lecture we studied those ideas of how to compute step length using desired velocity. Okay, Rybert controller is what we called it. And that is a powerful way to decide step length. And if you can decide step length, you know the position of the next step. And you can do it for the whole trajectory, maybe. So, in fact, it is not necessarily a completely crazy idea that you would have step length from a good source. That is a possibility. That is a possibility. So if you have your sequence of steps already given to you somehow, then it is perfectly reasonable to just fix them and not change them during, for example, MPC. That's what you will see done in this lecture. That's what people who are proposing the methods of control we're going to study here are doing. Okay. All right. Now, this is still not enough. This is still not enough. For us, what we want to do further is we want to linearize rotations. Okay, we want to linearize rotations. So this equation that I wrote here, this equation is not linear, and it is not made linear by assuming that R sub I is somehow fixed. You have to further make it linear by doing something about the left-hand side. And here is one way to make it linear. Let us look at it. First, let us introduce three-dimensional parameters. So like parameters in 3 dimensions, 3 numbers that would encode orientation. You can think of it as Euler angles. Okay, it doesn't have to be Euler angles. It can be anything like Euler angles. Just 3 parameters that encode orientation. Okay. In this case, I mean, I think it is fair to say that this is Euler angles. Okay. Now, we say that the derivative of those parameters would be connected to angular velocity in a linear fashion. And the coefficient of this linear connection is rotation matrix. So basically, you could say that the derivatives of those angles related to derivative of angular velocity by this rotation matrix. If in your case you decided on your parameters in some other way, your formula is different, good for you, no problems, right? It's almost always important again to double check. Equation 3 is not a very difficult equation. You can derive it yourself. Maybe the way you you defined your orientations, you would have R transposed here. It's very easy to make such a mistake, and then you'll be debugging for a very long time. Just rederive it. If you're going to implement it, just rederive it, right? You decided on your 3 parameters here. Let's say it is, what do we call them? Like aviational angles, rho, pitch, yaw. You can find in literature how they're connected to a rotation matrix, or how the derivative is connected to angular velocity. But you can also just very simply do some differentiation, and you would find all of this. So basically, this is a standard topic in classical mechanics. Don't take it from like a paper. Like as writers of this paper that we are following, they would present you the way they did it, right? My recommendation, strong recommendation, is if you feel uncomfortable with something there, like it doesn't feel obvious to you, go through mechanics, rederive it. Those are simple things, and then proceed. Okay. So I'm not spending too much time on this, but I just want to point out that these Euler equations and many other things can be easily derived. All right. Now, next one is kind of like a little bit similar. So what we have here is inertia now expressed in global frame times v dot, and we claim that this is equal to the sum of torques. This is a linearization, okay? This is a linearization. I'm not saying that this follows directly from the original equation. What I'm saying is this is a linearized model, okay? All right, so this is what the authors of the paper propose. They have a couple paragraph on justifying this. Check it out, right? Well, what I want to point out is that this matrix here is given as this conjugation of inertia matrix in local frame. So your local frame, your inertia matrix is constant, right? In global frame, it is not. So what you have to do to convert from local frame to the global frame is conjugate, in this case, by a rotation matrix, right? And that would give you this guy, okay? All right, well, this is the idea. The way I would present it in this lecture is we will assume for when we compute MPC, we will assume that R is constant, okay? This would allow everything to be a quadratic program, okay? We would assume R to be constant. How do we know R? Well, the same way as we know steps for it. We have to do some kind of guess. So in advance, we have to know, roughly speaking, the orientation of the body as it goes from place to place. A guess is sufficient. We don't have to know it exactly. It's not going to be extremely important to know it exactly, but we have to have a guess of orientation of the body. This would come from a heuristic, same as the steps came from a Rybert controller, which is a heuristic, right? Same R would have to come from heuristic. But importantly, it is constant. So this is constant, and this is constant. Therefore, this is constant. So those are not decision variables. Those are constants. They can change over time, but they're predetermined. They're not decision variables for optimization, is what I'm trying to say. Okay, all right. So this simplification now allows us to treat rotational dynamics as two first-order ordinary differential equations. This is ODE for parameters theta. This is ODE for parameters omega. Now it is simple, and those ODEs are also linear. They happen to be linear. Great advantage. Okay, good. Now, finally, after a great anticipation and all those weeks of suffering, we can look at our MPC. So this is our beautiful result, our beautiful MPC produced. This is not like the final form. We will see next slide the final form, but that is the meat and potatoes of this MPC. We will see. This is what people use to control actual quadrupeds. So let's look. We have to discretize our dynamics, right? As you can imagine, for MPC to work, writing it in continuous time is not easy and necessary. So instead we discretize with a time step dt. And the dynamics looks like this. X sub k plus 1 is equal to ak xk plus bk fk plus g. Those hats indicate basically that these vectors would have specific dimensions. Those vectors are reused very often, so it's just to indicate that dimensions here are MPC dimensions. Okay. All right. So let's understand what xk is. Xk is rotational parameters, position of the center of mass, derivative of the rotational parameters, the derivative of the center of velocity of the center of mass. Okay. So this is basically what this is. Here I could have put just omega, by the way. Wait, let me just double check. Did I do everything correctly? Did I do everything correctly? I think yeah, I think this is the type of here. It should be omega. I think it should be omega. Okay. So here should be omega, I think. We'll double check in the lecture, but I think it should be omega. Okay. My apologies if this is a type. I think this should be omega. Okay. All right. So x is orientation, position of center of mass, angular velocity, and velocity of the center of mass. F hat is a combination of all reaction forces that act on a robot during this step number k. Okay. So let's say you have 3 feet on the ground, it will be 3 reaction forces. Let's say you have 4 feet on the ground, it will be 4 reaction forces, F1, F2, F3, F4. They are, of course, different on each time step. So those forces will change on each time step, right? Okay. G here is just a vector of zeros and gravity force, which is, like you can say, gravity acceleration, which is 9.81, right? Basically, that's what it is. Okay. Now the most interesting part. What is A? Well, A is discretization of the Newton equations and Euler equations. So, for example, what is it? It relates the derivatives of each of those elements in X with the elements in X. Okay, but remember we here deal with discrete equations, so discretization. So we will have those things too. Since it is discrete equations, we would have those i's on the diagonal. Okay, basically it says next x would be equal to the previous x plus something. So for example, next orientation is equal to the current orientation plus r times omega times dt, right? R times omega is, remember, is delta theta, oh sorry, theta dot. So theta dot times dt is the difference between next theta and previous theta. So this is how you can read it. Okay, next one. What is next P? Next in position of the center of mass. What is the current position of the center of mass plus velocity of the center of mass times dt. Okay. What is the next omega? Well, the next omega is the current omega. We say that the omega does not depend on any other coordinate. It's not influenced by position, it's not influenced by velocity, not influenced by orientation. Okay, same is true for velocity. Velocity is not influenced by anything. That is in terms of state coordinates. Now let's look at the control matrix, which is something that we use to kind of move forward our MPC. Okay, so what is here? Well, here is this matrix has like rows of zeros here and here. What do those indicate? Well, they indicate that the next orientation and next position of the center of mass are both not influenced by the reaction forces, right? Since it is reaction forces that multiplied by B. So that makes perfect sense, right? Forces do not influence position or velocity. Forces influence velocities. Position orientation. They influence velocity or angular velocity. Because we have second order system. So this second order means that positions and orientations are not influenced by forces. It is the derivatives are influenced by forces. For continuous time, it will be the second derivatives, right? Acceleration and angular acceleration. That's what will be influenced. But for discrete time, we have like next velocity will be influenced. Next angular velocity will be influenced. Okay. How are they influenced? Well, here we can see how. So here what we see is force F1 will be multiplied by R1. This square brackets with a cross sign is a skew symmetric representation of a vector. And what it is just a matrix way to write cross product. So R1 in the brackets with the cross sign times F is the same as R1 cross F. Okay. It is just that it is always possible to rewrite cross product as a matrix vector multiplication. We call it skew symmetric form. Okay. If something of it is unclear, pause me and I will answer a question. Okay, now this thing is multiplied by I inverse. What is this I inverse? This is inertia matrix. Why is it here? Well, we wanted to avoid putting it in like here, for example, where it could have been if we just left it where it was. So instead we divided the whole equation by this inertia matrix, and it ended up only here because that was the right hand side, used to be a right hand side of our Euler equation. So when we divided by it, we got it here. Okay, and it is multiplied by dt for the same reason as this is multiplied by dt and this is multiplied by dt. Right? Discretization. Okay. Now, finally, what about the velocities? Well, velocities is the same. It's just that next velocity would be equal to like previous velocity plus sum of reaction forces multiplied by dt divided by mass. So this is just a Newton equation. This is just a Newton equation. That is it. That is all of this complexity. That is just a way to write it out in this linear form. Gravity acts, of course, on velocities. Also, I think here we miss multiply by dt. I think it should be multiplied by dt also. Yeah, should be multiplied by dt here. Two typos on this side. Omega here and g multiplied by dt should be. Okay, all right. Now this is discrete dynamics. So how does it become MPC? Well, like before that, we just need one last small detail, and that is each reaction force. We can rewrite it in this component-wide representation, where we have 3 components of each reaction force, and if we are lucky, we can write our friction cone like this. What do I mean by if we are lucky? Well, if the surface on which we move is horizontal, then this is a perfectly reasonable representation of the friction cone, assuming that z direction is orthogonal to the surface, right? If you are walking on a non-horizontal surface, then you would have to choose your coordinate system, in a way such that z would be orthogonal. But if you do that, then I have to ask you if you took it into account in your MPC. So here we have some issues. I would recommend to again be careful. But let's say you walk on non-horizontal surface. You can just rewrite it the friction cone in a more complicated way. It's not going to be too difficult, right? It's going to be just normal reaction. Remember, right? Normal vector times reaction force times mu has to be bigger than tangential matrix times projector into tangent space times f, right? So let me write it out so you remember. Would be something like pf less than equal to mu times n times f, right? Something like this, where p would be projector onto the left null space, right, of n. So it would be something like I minus n transpose, something like this, right? We had a whole lecture on this. So this is how you could do it. This is how you could do it. So this equation 6 and 7 is definitely not the reason to copy it. Make sure your the surface on which you walk actually allows you to represent your friction cone in this way. This is just a convenient way to linearize it without doing anything. It's like rectangular linearization. Remember, at the end of the lecture, we saw it. It's going to be like a square with 4 sides, like a pyramid, I could say. Very convenient, very nice. But of course, only works if your z direction is conveniently chosen. This would be second order cone constraint. And you remember again that this is not necessarily the most easy way to work with, because second order cone, instead you can linearize it, and how you can linearize it we discussed in the lecture. So plenty of ways to do it. You don't have to do it this way. Let me go back. You don't have to do it this way. You don't have to do it this way. You can but you can. Both of them are fine. You can also just do linearization around your actual normal direction. But it is quite typical to walk on horizontal surfaces. And for horizontal surfaces, 6 and 7 are very reasonable. So yeah. And even if your surface is slightly non-horizontal, let's say it is very slightly inclined, well, if your friction cone is sufficiently conservative, it doesn't matter, right? It's perfectly fine. So unless you walk on something relatively steep, 6 and 7 appears to be fine. All right, I will define this as f hat is in the C calc, right? C cal, cal for calligraphy. So you remember, right? This is like the calligraphic C. For those of you who are not familiar with the LaTeX, LaTeX calls math calligraphy. All right. So calligraphic C would it describes this friction cone. All right. Now we have every step that we need. We have discrete dynamics. We have friction cone. Now here you go, MPC. But the main one was this. Like as soon as we had this, everything else was easy. So let's look at it. This is a cost function, where we say, okay, let's ask that the next x would be as close as possible to the reference x. Again, where do we get this reference from? From the same place where we got our r, from the same place where we got our step, from some heuristic. Those heuristics, you can easily come up with them. The step length, as I suggested, is nice to get from Rybert if you can. But maybe you had a trajectory planner offline. Maybe you have a library of gates and you just run this library to produce your gate. Maybe something else. I don't know. Maybe mockup. Like you, for a bipedal robot, it's conceivable that maybe that's what you used. Maybe something else entirely, right? Maybe even neural network produced your desired gate. Okay. You know, possible heuristics are plenty. But here you just say, okay, next X should be as close as possible to the reference X. Since it is MPC, it doesn't invent new gates. That is not the forte of MPC. So you have to provide it a reference for it to be successful. Here, the original writers propose to, like the authors of this paper, propose to minimize f of k instead of a reference, because probably they didn't have a reference. They thought that finding a reference for this would be difficult. So they propose to just minimize the reaction forces. Fair enough. No, like, no judgment on that. Of course, usually what you prefer to do is to minimize difference from the reference, like here. So if we had the reference here, it would be nicer to minimize the difference. Why is it nicer? Because the difference can always be zero, right? Or almost zero. Whereas this guy cannot be zero. As you imagine, your robot is going to walk, and the reaction forces are going to be like the sum of reaction forces at least should compensate for gravity. So it's not going to be zero. So if you could provide a reference here, for example, maybe the sum of reaction forces is always equal to what gravity does, maybe it would be nice. I'm not sure. But this is what is provided in the original paper. So we just reproduce it here. Subject to discrete dynamics, and subject to friction cone. Please notice that this norm here is a weighted norm with a weight matrix Q. It is defined as Q times, X times Q times X and square root. Okay. Well, this is how the norm is defined. Those are weight matrices. Right? So this formulation Q and R, the choice of names, should remind you of LQR, right? It is a classic. We say we have separate weight on accuracy, separate weight on control actions. We want as little as possible control action and as high as possible accuracy. Accuracy here is like the opposite of error. So smallest error, smallest control action. And we choose Q and R to be different, which would influence us being more lazy or more accurate, you know. Okay, but remember, this is a linear, this cost is quadratic, the constraints are linear, so they behave very similar to LQR. And if you ever try to tune LQR using Q and R, you notice that it is not extremely responsive. It is not like pole placement. So you have to be prepared that Q and R here is not going to be easy to choose them. And the problem is not going to always be responsive to them, right? You have to be careful, is basically what I'm saying. But of course, it provides you plenty of opportunities to tune your cost. So maybe, for example, you place more importance on tracking the position of the center of mass as opposed to maybe angular velocity. Maybe angular velocity you don't really care about in terms of control error. Okay. Now, this MPC can run at 40 hertz, so 40 times a second. This again comes from the same paper where this was provided. This means that we could get desired reaction forces at this speed. So the output of this paper is X, remember, X and F. So desired reaction forces and the reference trajectory. That's what we get for running this MPC. And we can update it 40 times a second. 40 times a second is very low rate for control, but a high rate for MPC. So for MPC, it is fast. For control, it is slow. So we cannot plug this into control. It's going to be too slow update rate. We are going to be unstable for the reasons related to lag and so on. But as MPC, it is fast. It produces a reference quite fast. Okay. Now we can use these reaction forces to compute torques, joint torques. Let's see how it's done. Before we do you have questions about MPC? Okay, I assume no questions, so let me continue. So to compute torques, we use what the original authors call whole body impulse control. Whole body impulse control. The way I understood their proposal, they see it as a combination of two things that I see as quite different. One is task prioritization, which is basically like inverse kinematics that takes into account dynamics of the robot. And second is QP-based online solver that computes torques. So I will present only QP solver. The task prioritization, like dynamically aware task prioritization, the formula you can find in the paper. The derivation, though, is quite involved. It would require at least one lecture. So if I am very interested, we could discuss it, but it would take a whole lecture to derive. This task prioritization is not easy to work with. It is clean, nice. The results are beautiful. The derivation is very pretty, but it's long. It's not 5 minutes. So here we will omit this, and we're only going to discuss the QP. But basically, you can think of it this way. So what they want is you have inverse kinematics, which provides you desired position, velocity, acceleration. And you have a QP, which does something that we're going to see in a second. But yeah, inverse kinematics, I think on some basic level, you understand it. The difference between your basic inverse kinematics and what the original writers of the paper propose is that they wanted to prioritize certain tasks over others, so that the inverse kinematics is going to be solved exactly for some tasks and inexactly for others. Okay, all at the same time, and the inverses are taken not to minimize least squares, but to minimize some inertially weighted least squares. Okay, so that is the idea. Okay, okay. Now to start with the QP formulation, what we have to do is to write manipulate equations that you have seen previously. So here they are. The difference is that I divide my coordinates into baskets. One basket is floating base coordinates. Another basket is joint space coordinates. Okay. Floating base is 6 coordinates, like angles, 3 positions of the center of mass, for example. Notice that floating base coordinates associated with 0 torques, so no joint torques acting on floating base coordinates for walking robots. I'm not saying that it is inconceivable that joint torques would act on your floating base coordinates. I'm saying that for almost all walking robots that you encounter, it doesn't happen. Okay. So joint torques don't act on those. But they act on every other one. So almost all robots that you work with, in particular, all quadrupeds, their joints are all actuated. They don't have passive joints. So here you have tau. So the joints are fully actuated. Okay. And here is generalized reaction forces. This, remember, is Coriolis and normal reaction for inertial forces. This is gravity. Okay. Now, here is how this controller looks as a QP. So let's just study it carefully, line by line. So what they propose is to minimize some quadratic cost. We'll go back to what it means in a second. Subject to. This appears to be like our manipulator equation on left-hand side, but is multiplied by S. What is S? Well, S is a floating base selector. Okay. So it means that when we multiply by S, we cut off all the equations that have to do with joint space. So basically, we only leave first 6 equations. As simple as that. Imagine you have a list of equations, you cut everything below 6. First 6 equations you keep. Why first 6 equations? Well, because remember last slide, we placed our coordinates in 2 bins, one bin for floating base, one bin for joint space. So that's why. So first six equations are floating base equations because we chose our coordinates this way. Okay. Now, right-hand side looks like this. So this is, let's look at it one step at a time. So this is our contact Jacobian. This is our selector matrix. Everything fine. Here are reaction forces. And our reaction force, we represent them as a reaction force that we got from MPC. Okay. So what we saw previously at a 40 hertz. Okay. So a reference for reaction forces from MPC plus delta F. Delta F is a adjustment that we make online. This adjustment is part of what we minimize in our cost. So basically, we want to adjust as little as possible. Okay. But we allow adjustments. Now, where are the tau? Well, the tau actually goes away because, let's go back. Tau times selector matrix is 0, like this. First 6 equations here is 0. Everything else is cut off by selector matrix. So S times this is 0. Okay. Next, what we want is to make sure that our acceleration is equal to our desired acceleration. Desired acceleration, you can get it from inverse kinematics. In the original paper, it comes from this task prioritization inverse kinematics. If you really want to, you could imagine it coming from MPC, but definitely not in practice. Like in just for your understanding, you can imagine that this desired stuff comes from MPC, but MPC is too crude. So you can do much better by, and especially it only gives you the first 6 coordinates. So joint space is much more than that, right? So so this somehow has to be something else. And in the original paper, there is just a recipe of how to do it, which is a good recipe, and you can follow it. It works in practice. It is a nice recipe. Okay, so desired acceleration plus adjustment. Again, adjustment, but now for accelerations. So we have a desired acceleration, but we allow for adjustments. But we want to adjust as little as possible. So that's why we get, again, this part where we minimize quadratic form of this adjustment. Okay. No, and finally, we insist that our reaction forces lie in the friction cone. That is it. That is it. So this is what they call whole body impulse control. Essentially, it's just manipulate equations, cut like in such a way that we only have first 6. So the ones that are corresponding to floating base coordinates. We allow adjustment of accelerations and all accelerations, not just floating base accelerations, all accelerations. We allow for adjustment of reaction forces as compared to MPC. accelerations we adjust as compared to inverse kinematics. And we solve it online. Okay, let's see the discussion of this equation. So this controller can be solved at 500 Hertz. So much faster than the previous one. This is already good enough to be used for, let's say, control. You see at the end of the slides why I say, let's say, okay. But it is very good, it's a very high frequency. So the result is those adjustment variables. When we solve, we get this adjustment variables. Okay. Now, with that, we can construct our actual acceleration and our actual reaction forces. Knowing them, we can compute tau from our manipulated equations. Because manipulated equations is just, here's what used to be a left-hand side, here is our generalized reaction forces. We combine them, we get tau, right? So it's actually very easy. Or to be fancy, we could also just project all of this into joint space with another selector matrix. It would have been cleaner, maybe, but yeah, it doesn't matter. This 0 should remain 0 in any case, because we got all of this from QP. So yeah, in practice, you probably will use a selector matrix to select last n equations. Okay. Okay. All right. So this is how you compute torques. Please notice that what happens here is that you solve QP to find correct accelerations and correct reaction forces, even though reaction forces, you previously got them from MPC. So MPC gave you reaction forces. Then after that, you still have to correct them one more time. That's how it works. That's how it works. The whole role of MPC previously was to adjust for the fact that you have to step multiple times, and over all those multiple steps, you may have to redistribute how you gain and lose energy, you could say. Sometimes some of the steps would be long steps, some of the steps would be short steps. This is the type of information this QP doesn't have. This QP knows the reaction force that you have to produce currently, and it knows what acceleration you have to produce currently. What it does, it just adjusts those two numbers, because maybe you wanted acceleration and maybe you wanted reaction force, which together don't work well. Like you wanted too much acceleration for too little reaction force, or something else, you know. So basically, you can think of this QP as adjusting expectations that come from inverse kinematics on one hand, and MPC on the other hand. Okay, good. Now let's look at the big picture. Let's look at the big picture. So I hope you can see this slide well. Basically, what we saw today was model predictive control running at 40 Hertz, okay, which was basically used to run whole body impulse control at 500 Hertz. Okay, that's what we discussed today. Now, that produces torques. Torques, tau, can be then fed into a PID control as a feed forward. Okay, if you remember some basic like robot control or mechatronics or whatever, the way PID control often is done, you have a part which is feedback, where you have control error multiplied by gains, and feed forward, which is just a constant component meant to compensate for something. So this will be a feed forward of your PID. And your PID would have a feedback loop, which would basically be just your, inside your motors, you would have those loops. Those loops can run at 40 kilohertz, extremely fast. This is only possible because the electronics and everything is in a separate like cases. They are not going through the main computer, etc. It is because everything is modular. Everything has like the sensors here physically in the same place as the motor, in the same place as the controller, which takes the readings of the sensor. There are no long distance communications. There are no buses through which the signals go, where you have like multiple senders, multiple receivers, etc. Everything is very tight. It's a small control loop. That is why you could achieve those impressive performances. Okay, 40 kilohertz. Okay. Now, these desired values would come from the same way where your desired value came that you used in the whole body impulse control. So from inverse kinematics, basically. Okay. Now, what we didn't discuss? Oh, first of all, previously we discussed, remember, how we could use Rabbit to design gates and so on. Well, you could say that this is, roughly speaking, that kind of stuff. Remember, see, we have this like speed command here. Maybe Rabbit sits somewhere in this gate scheduler, step planner, something like this. This is a material from the previous lecture, like all of this mess. In general, you could say that this part is usually not crystal clear. What we discussed today is a crystal clear part that is very clear, very nicely designed, and so on. This part here, gate type, gate scheduler, step planner, all of this is not crystal clear. Why not? Well, because it has to do with the terrain, and terrain can be flat and nice. It can be not flat and not nice. Then sometimes you'll want to do footstep adjustment. Sometimes you want to ask yourself even if you can even step on something. Sometimes you want to jump over something, etc. So all of this is not a clear picture. The type of control you're going to use here depends very much on the task you're trying to solve, and so on and so forth. So this part with a lot of arrows and dark green splotches, that is not a well-solved part of robotics at the moment. And you can kind of imagine this, right? It's one thing to control a gate which is already given to you. Another thing is to come up with a gate which specifically addresses the needs for a specific situation, right? If you remember your first time when you did, like, let's say, hiking on a mountain, I mean, like small mountain, right? Like hill. I'm sure every one of you at least try to go uphill in a, let's say, outdoors environment, not on the paved road, but maybe on a stony hill. First time you did it, you noticed it is quite different from walking on the asphalt, and it took you a little bit of while to adjust, maybe half a minute, but still, was different. Robots have to adjust too, and it is not obvious how it should be done in terms of like matrices and so on, right? So it should make sense for you that this appendix here is the open area of research. All right. Now, also what we didn't discuss is this part here, robot kinematic and dynamic model. This usually refers to some instrument, like a Pinocchio, for example, instrument which would provide you matrices, H matrix, A, B matrices, etc. You often need them, and they need to be evaluated fast. Like you don't want them to be computed in a slow fashion. This is a separate issue, so we didn't discuss in the course. But importantly, those things can be computed fast using third-party software. Okay. Now, the big elephant in the room that we ignored is state estimator. You remember we had a lecture on state estimation, how it can be done in minimal coordinates. Well, that is nice, but that is nice if you use minimal coordinates for your control. What people do usually is they try to do Kalman filter style state estimation instead. They don't like what coordinates you use is a open question. I don't want to say that this is a solved problem, etc. But essentially, what people come up with is treating like this floating base coordinates in a way similar to how you would treat, like, say, coordinates of a drone. So in what basically as coordinates on SE3 group, the group of transformations, like rotations and translations. And they employ what we call Lie theory sometimes. That depends on the authors. Basically, Kalman filtering is kind of like the spirit of what they do. But yeah, what some people do is they employ Lie theory to minimize the discrepancy between, like, to basically linearize, you could say, this representation. Lie theory allows you to treat coordinates which are essentially nonlinear, right? Orientations, positions, kind of like to treat them linearly. It's kind of like going from a globe to a map of a globe, right? From a surface of a globe to a Mercator projection. This kind of idea. This is a mathematically difficult new area, extremely interesting, and is one of the most successful and dynamic areas in robotics, in working robotics right now. So very interesting stuff. People try to use this approach also for this, right? For model predictive control, for what here was done as a whole body impulse control. So it's interesting. There are possibilities, but state estimation we didn't cover basically because it is complicated as a thing in itself. But the work there is successful, very interesting. Lucky for us, it is often it is often done as a software package, so it is possible to integrate it into your system without understanding Lie theory. I know this for a fact because I have seen it done in practice. I have seen people who did not study Lie theory, but were able to successfully use modern state estimators. Of course, it would be nice to understand Kalman filtering and everything else, but I'm just saying that it is possible to use those instruments. But yeah, this is a big elephant in the room that we didn't cover in the course. All right. As you see, this picture looks complete, as if we didn't have anything else to cover. So of course, a little bit is still left, like sensory perception, vision, like how do you react to environment, especially when the environment is challenging. All of this is also we left out. You could say that we focused mostly on like this part, right? Like relatively high level control. So out of everything that we could have focused on, we focused, let me use a difference. We focused mostly on this part here, right? And maybe a little bit on this. It's just a little bit of this, right? Low level control that is done very nicely here with PID is also its own topic because there the main issue is speed. You have to be fast. So the speed of communication, etc., is quite important. Like you have to achieve those very high very high frequencies, update frequencies for successful control. That is also a practical consideration that people take. All right, but not to like turn this lecture into a review of every single problem that quadrupeds face. Like on the to stay on topic of what the spirit of this proposition that we studied today, and the proposition is again by Tim and co-authors, is we do MPC on a very much simplified model, on the potato model, we call it. Okay. Then we do a separate QP control on a whole body model, so manipulator equations, and we do corrections there. Like those corrections allow us to correct for reaction forces and also for acceleration with center of mass. And from that, we can compute PID control and put it directly into the actual robot. Okay. Let me see. So this is the paper. This is the original paper that was done by Kim. Let me see if I can quickly show you. So this is the paper, right? And let me just show you how much of it you can read on your own without much trouble. Okay, I just want you to kind of feel more at ease with those papers. So here's our familiar picture. Here they discuss their simplified model. Okay, so this is something that you already saw in the class. Right? They have their own justifications that you have to listen to, right? And you have to evaluate, etc. But yeah. Here's your apologies, even my mouth today is dying. Everything is dying. So this is manipulator equations. They use this strange notation with A instead of H, which I mean, considering that they use A here as well, I don't know why they want to do it. Okay. This manipulator equations, right? B is what we call C times Q dot, is inertial parameters, inertial forces. Okay. Now, here is their justification for going to a simplified rotational model. So, and notice that they have this subscript Z. This is because they specifically discuss which type of orientations that they allow. They only allow yaw. Out of raw pitch yaw angles, they only allow yaw. That's additional simplifications that they made. But yeah. Okay. Now here is the what I discussed previously. You remember, from this we go to this, and we do it by somehow ignoring this additional part. Okay. And here is their discrete dynamics. We saw it on the slides. Okay. And this whole thing we saw. This is cost that we saw, and this is the friction cone constraints. Okay. All right. Now, this may look slightly different from what you remember, but this is basically your Rybert controller. Here, the difference is they account for rotation. So they have additional components that have to do with rotation. Like this component has to do with the rotation of the body. This component has to do with the fact that you have angular velocity, possibly, right? but essentially this is just basic geometric considerations plus Rybert. Like you can imagine if you are going to rotate, your next step has to account for the fact that your shoulder rotated, right? So of course. All right. Now the big part that we did not discuss is this. This is the task prioritization method. Okay. Together with this part here, like all of this is like it looks very neat on the paper and you can just implement it, it would work. I'm pretty sure there might be a typo here. I don't remember for sure, but like this mostly should work, I believe. Yeah. So just the reason why I say they might be typo, etc. Remember, we are looking at archive, not at the published version of the paper. So sometimes typos happen. We verified all of those equations, and during verification, we sometimes felt like there was maybe a typo or discrepancy with the code. My point is not to say that the authors did something wrong. My point is to say if you're actually going to do any of this in real life, verify, 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 verify. Okay, never take something for granted. Always verify. And for this kind of stuff, the verification process is best done by derivation first. Extremely time consuming, but possible. In this case, if you're going to do this, you can ask me to share my notes on how I verified this. So I would be happy to help. But also you can look at the code. In their code, they actually write some of the stuff. And you can compare this to how you understand each element here. This is another way to verify, okay? Like with the research papers, you cannot just copy something and expect it to work. You have to do your own work to make sure that the result is correct and so on and so forth. Okay, so this we don't discuss, but yeah. Okay, and then finally, here's whole body control, right? It should just look familiar. That is what we discussed last. And this is what we discussed in how we compute our tau, okay? All right. And that's it. That's it. The rest is the results on running on cheetah robot. So you can see this is a paper which I would personally consider one of the foundational in the field if we talk about recent advancements, okay? So as far as the recent advancements go, this is one of the foundational papers, extremely important. But now you more or less can understand it, the whole thing. And so you can understand the other papers too. It is not like they are on a completely different level. That is kind of, if you want my message, to end the course. It would be probably impossible to cover everything in one course. Prerequisites are plenty, and advancements are plenty. Even if I covered, let's say, state estimation, there would still be perception. Even if I covered perception, there would still be reinforcement learning, if I, etc., right? There would always be more. But to actively engage with the field, you don't have to wait forever. You can also go ahead and start to interact with scientific literature. I have seen plenty of programmers who, without even a strong foundation in classical mechanics, were able to integrate successfully in the teams that work on quadrupeds and so on. So strong programming skills often compensated for lack of background, but with background, the kind of background you have, that is not such a that's not such a big problem anyway, right? Somehow it feels to me that this field, currently at least, requires strong background in programming, not as in like some kind of master level competences, but at the very least, familiarity with software development, the way it is done right now. Like it is heavy on using packages, on integrating software, on testing, and so on and so forth. It's not easy, right? But lucky for you, you come from the software-oriented university. So again, you're in a good position to integrate into this field. If you do, good luck. I would hope that the course would have been useful to you. If you have any questions about this now, later, before the exam, after the exam, in general, I'll be happy to help. I'm not sure if I would always be able to help, but I would be happy to try, you know. So even after the course is over, I'm always open to discuss with you, or you know, whatever little advice or help I can give, I would be happy to do it. All right. With this, this is our last lecture. This is over. The course is over. Will we see each other during the Q&A before the exam? Yeah. Thank you so much for speaking out. It was a long 11 weeks. Thank you, guys.
Thank you, Professor.
Thank you, Professor. It means a lot.
Thank you, Professor.
Thank you very much.
Thank you, guys. Right. We'll see you.
Goodbye. Have a nice